This lecture, or talk, has to do with explanation of a gyroscope, gyroscopic motion. And you've all seen this is a sort of toy gyroscope. And the explanations that are posted on the internet, when you look up gyroscope, explain it in terms of momentum vectors and the motions and those sorts of things. But they don't explain it in terms of the laws of motion, of Newton's laws of motion, and the property of inertia of a mass. And what I'm particularly talking about is the using the second law of motion, which is that the force applied to an object will cause the object, the mass of the object, to be accelerated. Similarly, if there is an acceleration, then there has to be a force applied. And that's what we're going to look at. So this just talks through the typical explanations are in terms of there's an angular momentum about this axis, this I omega, about that axis, and then there's rotation about the vertical axis, and that results in a moment about the horizontal axis in the M, okay? But that's not an explanation in any kind of real, that's just what the law says. And I've written it in terms of the gyroscopic moment. This moment about here is perpendicular to two axes, this axis and that axis. That's why the two normal signs. And it's the product of the moment of inertia, polar moment of inertia, angular rotation, and then the angular motion about the vertical axis. Okay? So, and that's essentially what this does. You can stop the video and read through these letters, and you can repeat it through these comments. But what I'm going to get to here now, very quickly here, is an explanation of the gyroscopic moment in terms of Newton's laws of motion. So, here is a gyroscope. There's the picture there, the disc, and it's rotating this direction, and that axis, that there about this axis, as you can see. And then the intent is we'll look at what happens when we turn it this way. So that this is the head of an arrow indicating that this side of the disc, in addition to rotating that way, is being turned. And similarly, the tail feathers of the arrow are indicating that it's being turned in that direction, back into the direction of the plane. Okay? What we're concerned about is a mass which is going around. We just take one section of the mass of the gyroscopic disc and look at what happens to it as it moves from here over down to this point here initially, and then of course each quadrant. But as it's going like that, it's going around that at a constant speed because it's rotating. This is the direction of rotation. And if on top of that rotation is also imposed this motion here, this motion about that axis. Well, at this point, around at this point here, there's a slight motion forward. So if you tip it this way, you can see that about that axis, this piece is rotating a little bit. And then further out here, this is going to be rotating further, more because it's got a higher velocity in this direction about that axis because it's further from the axis. The angular motion is the same throughout. And the maximum velocity going this way is it's at the 90-degree point, at this point here. So if I am imposing this motion, and the mass is going through here, and it's the acceleration, the change in velocity is increasing, so it's actually being accelerated out of the plane here in this direction. There's going to have to be a force applied out of the plane. And that's what this is the point of the plane, so it's being pulled out like that. And similarly, when we get to this point, and the mass goes from this high velocity in this direction down to a point where there's no velocity out of plane velocity, then there has to be a force in this direction to decelerate it, and thus this positive piece here. And if you just complete the argument for this quadrant, you'll find the force that's required is in that direction, and up here, the force is this way. So, when you look at the directions of these forces that would be necessary in order that you could turn this like that, you see that there's a force in the lower quadrant down here, all going into the board, and above this axis here, their forces are coming out of the board, and thus there is generated a moment. So when you impose this, there is a necessary moment this way that has to be applied. And of course, that produces a back reaction, and you have to feel it and all that. But that's just accounting for where the forces are coming from. But the point is, that is the mechanism of how this moment about this axis is generated. Okay? Now, that's shown here in this diagram. There's the axis like this. This is the motion, out of plane motion, as I was talking about. And if you look down at the axis of the disk this way, that's what this is showing here, that there's got a velocity of that disk going in that direction. This is due to the secondary rotation. This is the primary rotation, and this is the secondary rotation up here. And that's that's that. And then these all just walk through what I was just doing here, going from 12 to 3, 3 to 6, and throughout. So again, you can go back and read those, but brevity, I'm not going to be particularly interested in walking through all of that for you. And so we end up with the fact that the imposed secondary motion, this secondary motion, out of plane, requires that this moment about, generates this moment about here, or it requires a moment about that point. Similarly, of course, in the reverse, if you apply this motion, it's going to want to rotate. And that is what happens when you have a person sitting on a swivel chair and they have a gyroscope or a big wheel of some sort spinning, and then they impose a motion on it. It provides them, it gives them this rotating piece. And it also occurs with bicycle wheels and wheels on a car, that when the wheel is rotating, and then you go around a corner, you can see that that's being rotated, either that way or that way, and then there's a gyroscopic moment. And you then have to lean into the curve, because that moment is such to kind of want to roll you out the other way. And thus, therefore, you have to lean into the curve in order to counteract this moment, this gyroscopic moment that would want to overturn you and tip the bicycle over. And so that completes the presentation. Hope you've enjoyed it, because it's an explanation that I've not been able to find on the internet, and but understanding it at that qualitative level will then help you understand that when you use the angular momentum terms, it's vectors. That's only just a representation of what's physically happening. So, thanks. Done.